Steel calculation for RCC slab. Step-by-step example. In the field of civil engineering and construction, the accurate estimation of materials is a cornerstone of successful project management. Reinforcement steel for RCC is a critical and costly component. Therefore, precise calculation of required steel is essential for budgeting procurement, minimizing wastage on site. This is a clear, step-by-step technical guide to calculating steel for a rectangular slab. We'll use a practical worked example. Methods are standard practice and adaptable to various slab sizes. Example slab dimensions: 4 meters in length, 3 meters in width. Reinforcement details are consistent in both directions. We'll use 12 mm diameter high-yield deformed bars. Spacing: 150 mm center to center. 4. Main reinforcement, distribution reinforcement. Final objective: total weight of steel in kilograms quintals, plus a simple Excel setup to automate the process. Process is methodical, broken into stages. Stage 1. Understand the layout of steel bars, main bars, distribution bars. Start with an introduction slide. Steel calculation for RCC slab. Step-by-step example. Then show a simple drawing of a rectangular RCC slab of size 4 meters by 3 meters with 12 mm diameter bars at 150 mm spacing both ways. Visually highlight the drawing and explain. Main bars in one direction, distribution bars in the other direction. Stage 2. Calculate quantity of bars in each direction. Number of bars. Total distance, center to center spacing. +1. The +1 is crucial. It includes the final bar and ensures full coverage. First, calculate main bars. Main bars length, NARTH 4m, i.e. 4000 mm. They run across the slab width. Slab width, NARTH 3m, i.e. 3000 mm. So total distance, NARTH slab width. Number of main bars, NARTH 3000 mm, 115. +1. Number of main bars, NARTH 20 + 1, NARTH 21. We need 21 main bars. Now, distribution bars. Distribution bars length, Sabra 3m, i.e. 3000 mm. They run across the slab length, Sabra 4m, i.e. 4000 mm. Total distance, Sabra and slab length. Number of distribution bars, Sudden, 4000 mm, 150 mm. +1. Number of distribution bars, Wonga 26.67, +1, Plava 27.67. You cannot place a fraction of a bar on site. Therefore, we must round up to the next whole number to ensure coverage and spacing, or 150 mm. So we will use 28 distribution bars. This step highlights a common point of confusion. Remember, to count bars in one direction, use the perpendicular slab dimension. Visualize the slab. Number of bars. How many fit side by side across width or length? This gives the basis for total steel length and avoids ordering errors. An incorrect count here will cause a shortage or a surplus of steel on site. After calculating the quantity of bars, the next critical step is to determine the precise length to which each bar must be cut. The cutting length is not simply the span of the slab. To ensure that the reinforcement bar is properly anchored into the supporting beams or walls, and to prevent slippage under load, hooks or bends are provided at both ends of the bar. Hooks, bends. This is a requirement as per standard codes of practice for detailing. For this example, we will use a standard 90-degree hook. The additional length required for such a hook is typically taken as 10 times the diameter of the bar, or 10 times dia. Let us first calculate the length added by the hooks for our 12 mm diameter bars. Hook length 10x dia. Hook length 10x 12 mm, 120 mm. Since each bar will have a hook at both ends, the total added length for hooks per bar will be 2 times 120 mm equals 240 mm. This additional length must be added to the clear span of the bar to get the total cutting length. It is also important to note that for practical calculations, we often deduct the concrete cover from the slab span, but for this illustrative example, we are using the full span for simplicity. Now, we can calculate the cutting length for a single main bar. The main bars span the 4000 mm length of the slab. Cutting length per main bar equals span of main bar plus 2 times hook length. cutting length per main bar equals 4,000 mm plus 240 mm equals 4,240 mm. To make further calculations easier, especially for weight estimation, it is convenient to convert this length back to meters. Cutting length per main bar equals 4,240 millimeters divided by 1,000 equals 4.24 meters. Each of the 21 main bars will need to be cut to this exact length. Similarly, we calculate the cutting length for a single distribution bar. The distribution bars span the 3,000 millimeter width of the slab. Cutting length per distribution bar equals span of distribution bar plus 2 times hook length. Cutting length per distribution bar equals 3,000 millimeters plus 240 millimeters equals 3,240 millimeters. Cutting length per distribution bar equals 3,240 millimeters divided by 1,000 equals 3.24 meters. Each of the 28 distribution bars will be cut to this length. Having these precise cutting lengths is essential for the bar bending schedule, which is the document used by steel fabricators to prepare the reinforcement for the site. With the number of bars and the cutting length of each bar determined, we can now proceed to the final and most important part of the estimation, calculating the total weight of the steel. Steel for construction is ordered and paid for by weight, in kilograms or tons, not by length. The first sub-step is to calculate the total running length of all main bars and all distribution bars separately. Total length of main bars equals number of main bars times cutting length per main bar. Total length of main bars equals 21 bars times 4.24 meters per bar equals 89.04 meters. Total length of distribution bars equals number of distribution bars times cutting length per distribution bar. Total length of distribution bars equals 28 bars times 3.24 meters per bar equals 90.72 meters. The next sub-step involves converting these total lengths into weight. This is done using a standard formula that calculates the unit weight of a steel bar in kilograms per meter. The simplified industry standard formula is unit weight in kilograms per meter equals dia squared divided by 162, where dia is the bar diameter in millimeters. For our 12 millimeter diameter bars, unit weight equals 12 squared divided by 162 equals 144 divided by 162 equals 0.8889 kilograms per meter, approximately. This value means that every 1 meter length of a 12 millimeter bar weighs 0.8889 kilograms. Weight of main bars equals total length of main bars times unit weight. Weight of main bars equals 89.04 meters times 0.8889 kilograms per meter equals 79.17 kilograms. Weight of distribution bars equals total length of distribution bars times unit weight. Weight of distribution bars equals 90.72 meters times 0.8889 kilograms per meter equals 80.64 kilograms. Total steel weight equals weight of main bars plus weight of distribution bars. Total steel weight equals 79.17 kilograms plus 80.64 kilograms equals 159.81 kilograms. For larger projects and commercial transactions, steel quantities are often discussed in quintals. A quintal is a unit of mass equal to 100 kilograms. Total weight in quintals equals total weight in kilograms divided by 100. Total weight in quintals equals 159.81 divided by 100 equals 1.5981 quintals. For practical purposes, this can be rounded to 1.60 quintals. Thus, for our 4 meter by 3 meter slab, we require approximately 160 kilograms of 12 millimeter steel. This final figure is what would be used for procurement and cost estimation. While performing these calculations manually is excellent for understanding the process, it can be time-consuming and prone to human error, especially when dealing with multiple slabs of varying sizes. Microsoft Excel provides a powerful and accessible tool to automate this entire workflow. By setting up a simple template, you can input the basic slab and bar data and get instant, accurate results. First, set up an input section as the control panel. A1, slab length, M. B1, 4. A2, slab width, M. B2, 3. A3, bar dia, mm. B3, 12. A4, spacing, mm. B4, 150. A5, hook factor, B5, 10. This lets any slab be calculated by changing those 5 values. Next, calculation section with formulas. C1 num main, cha, B1000 B4 san C2 num dist, round up B1000 B4 san. D1 len per main to B1 plus 2B5 B1000. D2 len per dist, B2 plus 2B5 B3000. E1 total, len main sa C1 D1 E2 total, len dist for C2 D2 output section. F1 witty per M ash B3 1 Johnson 62, F2 witty main kg ash E1 F1 F3 witty dist key dishit E2 F1 F4 total witty key dishit to sum F2 F3 F5 total witty cubishir F4 100. Structuring the sheet creates a reusable professional tool. Change inputs, totals update automatically. This is smart construction management. Methodical approach ensures accuracy and efficiency. Audience, site engineers, quantity, surveyors, civil engineering students, contractors. Precision prevents. Over-ordering of materials ties up capital, creates storage issues. Precision also avoids. Under-ordering costly delays project downtime. Mastering this skill improves financial health and timely project completion. We'll show simple Excel formulas to automate the workflow. Download Excel template, link in description. Subscribe for more civil engineering tutorials.